In this video, we're going to look at a topic that is one of the tricky topics for AB calculus or calculus 1 students. Some people just get it easily, but some people just have a lot of trouble with this. And that is sketching derivatives given the original graph or sketching the original graph given the derivative graph. So the entire backbone of this, everything is based on the following idea. So the slopes of the original function are the values of the derivative function. And vice versa. And this leads us to some consequences. So for instance, if the original is increasing, then the derivative is positive. And for our graph's purposes, that means above the x-axis. And vice versa. Well, yes, conversely, if the derivative is above the x-axis, the original function is increasing. Almost inversely, but not quite inversely. If the original is decreasing, then the derivative is negative and below the x-axis, and all that stuff comes together. And if the original has a horizontal tangent, I guess it should go both ways, then the derivative is equal to 0, or it's going to be an x-intercept for the derivative. And so these are the basic ideas, and learning one way is pretty straightforward, but it gets difficult when we start going the other way, confusing which way we're going here. So we'll take it one way at a time. If you want to skip down to examples or skip back or anything, there will be links to the parts in the video in the description. So let's dive right in. Going from the original function to the derivative function. The idea is this. We are going to consider the tangent slopes and plot those slopes as points on the derivative. And let's look at two examples of this. The first one I'm going to do very slowly and methodically and try to visually show and explain the thought process. The second one I'm going to go through a little bit faster. I'm trying to describe more of how I actually do these problems. So, given the graph of f of x, right here, sketch the graph of f prime of x. And notice we aren't given the function. It's not a single equation or single expression. I actually made a piecewise function to get this graph. And here's what I am thinking. So I want to know what f prime is. So I'll do this. Now, on this graph, there's no scale at all, so I'll impose my own scale on here to be able to look at it more clearly and get some values that I think are reasonable values. So I'll just put this as the scale. This is actually the scale that was on the graph when I made it in GeoGebra, but it doesn't really matter. If you make it more or less spread out, you'll get the same thing, and I'll toss this same scale onto the derivative over here so we can see what's going on. Okay. And so what I'm going to do is this. I look over here, and when x is negative 4, I see that it's actually linear. So the tangent line will have the same slope as the line, and it looks like I have a slope of negative 1 here. And similarly, at negative 3, I'm still linear. Looks like I have a slope of negative 1, so the derivative will be negative 1. At negative 2, there's a corner, which means that the derivative is going to be undefined. But when I sketch this, and I'll remind us when we're sketching this, to the left of this, it looks like negative 1. To the right of this, it looks like maybe a 2 slope. So I'm going to use those to show what the jump is going to be, but it will be discontinuous there. All right, at negative 1, this point here, looks like I have a 1 slope. At 0, I have a horizontal tangent, so I have a 0 slope. At 1, this portion here is even, so it looks like I have a negative 1 slope at 1. At 2, looks like I have a negative 2 slope. At 3, I'm getting steeper, and you say, okay, I seem to see a trend. I'll say it's more negative than it was over here. This was negative 2, so I'll make this one negative 3. It's not that much more negative, but I better show that trend. I can't make this negative 2 or larger because clearly it's steeper down here. And at 4, I'll just go to negative 4 because it's even steeper. And all I'm going to do now is plot these points on here, because this having a slope of negative 1 means we have the point for negative 1 on our derivative. Same thing for this. All the way up to negative 2, it looks like I have the slope of negative 1, so I will have all the way up to negative 2, but not including negative 2, have a slope of negative 1. But then right afterwards, it looks like I jump up to a 2 slope, steeper than this negative 1 slope, and positive. So I'm going to go up to 2, but I don't actually have anything at negative 2. It's undefined there because of this corner. And then I just plot all these points. It actually makes a nice little linear function over here. The derivative looks to me like it was linear, so I'll plot these points. Again, this point here, just a reminder, is because at 2, it looks like a slope of negative 2, so I have the point 2, negative 2, and connect it up because it looks like it's nice and smooth throughout, so the derivative should be continuous over there, and that's what I get. Now, that's not the only way to consider it. This one takes a lot of time, as you probably just realized, so let's look at this a little differently. Different problem here. Same idea, different numbers. When I look at this, I try to look at it in pieces. So again, I'm talking about the slopes. Well, I can see from here up to this point, so I'll call this point, instead of giving it a number, I'll just call this the point A. I can see that the, so from negative infinity, let me actually make an infinity symbol, negative infinity, up to A, we have positive slope, but the slope is leveling off. It's getting less steep. So, but getting less steep. And so, on here, what that means, let me make an A here, is I start off with a positive slope, but it's getting less steep. It's getting closer and closer to 0 in some way, shape, or form. I don't know if it's linear or curved, but it's getting less and less steep, so we're getting closer and closer to 0. At A, we're horizontal, so because it's horizontal there, we actually hit the x-axis. From A up to, let's say, this point here, again, we're looking at slopes. I'll call this point B. So from A to B, it is a negative slope. But here's the next thing. From a to 0, the slope's getting steeper negative. And then from 0 to b, the slope's getting less steep negative. So I'll put a b right about here. And I will get steeper negative up to 0. So I'll go down like this. This is as steep as it gets. We're still negative, but we're getting less steep, so we're going to go back towards a 0 slope. And now, from B to C, so I'll put a C right here, we are positive slope at a faster rate, steeper. So it's going to be increasing positively. But at C, we have a discontinuity, so the derivative will be undefined. We have a jump here, so there is no tangent line. But you can see, to the left of C and to the right of C, it looks like it's about the same slope, so it'll continue from there. It'll sort of meet the same point, but we're linear here. So C to D, I'll skip down here a little bit. So from C to D, it is linear positive, and D onward, linear negative. At D, it's clearly undefined because we have corner, so derivative is undefined. And I'll put all that in here. Now, I think this stuff through as I'm graphing and just get the graph, so let me put D on this graph for me. And so linear means I have a constant slope, so now I get horizontal lines on my derivative, positive here, and negative onward. So that's the thought process I go through when I'm doing this. Now let's look at the other way. So what if I have the derivative function, I want to get back to the original function? So in this case, I use, or let's say this, not use, but find the value of the derivative, and then I'm going to use that to make the slopes of the original. So it's the exact opposite. But I want to note something here. Note there are infinitely many original functions given a derivative function. The derivative function tells me the slopes, but tells me nothing about where it starts or a specific point. So I can actually start at any point, and then I just follow the slopes from there. So, like before, I'll go through two examples. The first one, I'll spend a lot of time trying to get in the nitty-gritty of it, and then the second one, I'll try to explain a little bit higher order thought, what I go through to get there. Okay, so in here, I'll start off the same way, and I will say, okay, let's impose a scale on this so I can talk about specific points on here, and we can just try to make it as simple as possible, even though it doesn't get us the best understanding possible. And I'll impose the same scale on where my solution's going to go, where my answer will be. Okay, so here's the idea. I'm going to do the same thing, and I'm just going to look at h prime of x still. It's going to be the same table, or table setup that I did for the other one, and I'll go from -4 all the way up to +4. This table will be easier to get started, because I'll just look and say, okay, -4, -1. -3, -1. -2, 0. -1, 1. And then at 0 it's undefined, but on its way up to 0 it's increasing to 2. And after 0 it starts at -2, and then by 1 we're at -1. At 2 we are at 0. 3 we are at 1. 4 we are at 1. Okay, so just the values of the derivative went in here. And now I'm going to take these and I'll start somewhere. And let me just start here, okay? And I'll say, okay, I want a -1 slope. That's going to look like this. And at -3, I still want a -1 slope, so that's still going to look like this. Okay, notice I sort of set them up so I could draw a nice smooth curve. It's going to be straight at this point because we're constant, but nice smooth curve through this. By the time I get to -2, it's at 0. So I'm not going to go all the way down as if we're linear. I'm going to say, okay, if I were to smoothly get to that, my horizontal, my 0 slope would maybe be about here. And at -1, we're at a 1 slope. And again, I'm not going to go straight over. I'm going to say, okay, if I were curving up, I'd be back maybe here. And at 0, it's undefined. However, on the way to 0, we're getting steeper and steeper. So that undefined is going to end up somewhere over here. Now let me actually sketch this before we move on. So I'm just going to then sketch the curve that connects all of these tangent lines. And if I just wanted less than 0, I'd be done. Here's the fun thing about this. Since the derivative is undefined at 0, I can actually restart anywhere that I want. I could start back from this point, or I could start from any other point on here. And when we get much later in the course, this is why when we're solving a differential equation, I can only solve it in the continuous interval around my initial condition, because afterwards it could actually restart anywhere and still satisfy this derivative function. For simplicity's sake, I will start from this point. It's not going to be filled in because we have this discontinuity here, but it looks like I start with a -2 slope, or almost -2 slope, getting to a -1 slope when I get to 1, a 0 slope when I get to 2, a 1 slope when I get to 3, and now it's linear because I have a constant derivative here, so a 1 slope at 4, and so I have this nice little upside down seagull looking thing right here. So that's if I want to just consider point by point. Let's look at an example where I'm trying to think a little bit higher level. And I'll break it down still, but once you really get this, you'll be able to go through it much faster. So in here, I'm going to break this up into a few different things. So I'll call this point A. I'll call this point B. I'll call this point C. And you can see I'm sort of breaking this up. We have 0 here. I'm not going to give it another point, but I'm breaking this up into the parts where something's fundamentally changing about my graph. Okay, so I'll make this point D. This point, I'll give it the name F. I don't want to give it the name E as the constant 2.71828, so I'll make it F, and I'll go G here. So these are the X values where the derivative graph has some fundamental change that I'm going to want to address. And so, from 0 to A, not 0 to A, sorry, -infinity to A, I know that my derivative is negative, which means I should be decreasing. because the value's down here, but it's getting closer and closer to 0, so less steep as we go on. At A, derivative is 0, so I should have a horizontal. And let me start filling that in. So I'll put A here, B here, C here, we have 0, D here, F here, and G here. Okay, so in here, I start decreasing. Again, it doesn't matter where I start, so I'll just start up here. I usually like to start, if I'm starting decreasing, I'll start up here, so I try not to get off the graph. If I start increasing, I'll start down here. I made these graphs so they don't keep on going off in one direction, but it doesn't really matter. So in here, I start decreasing, but by the time I get to A, I should have it horizontal, because at A the slope is 0. All right, now from A to B, sorry, let me change colors, get this right. So from A to B, the derivative is above the x-axis, positive, so I will have it be increasing, and it's going to be getting steeper and steeper because the derivative is getting further away from the axis. So increasing, steeper and steeper. At B, it is at its steepest, because this is the furthest above the x-axis it gets. So from B to C, and this is where people start messing up. From B to C, my derivative is still positive because I'm above the x-axis, so I will still be increasing, even though the derivative itself is decreasing, but it's positive, which means I'm increasing, but it's getting towards 0, so it'll be less steep. And so at C, we hit 0, and that means I'll be horizontal again. So starting here, less steep, less steep, less steep, horizontal. And that's the process I go through. So I'll just walk us through it now. From C to 0, it's decreasing because the derivative is negative at a steeper rate because I'm getting farther and farther from the x-axis. I'm getting a bigger magnitude, so it'll be decreasing at a steeper and steeper rate. From 0 to D, it's decreasing at a less steep rate. When it gets to D, it will level off because the derivative is 0. From D to F, the derivative value is positive and it's getting further away from 0, so it'll be increasing at a steeper and steeper rate. From F to G, the derivative's value is still positive, so it'll still be increasing, but it's getting closer to the x-axis, so it'll be increasing slower and slower. When we get to G, it levels off because the derivative at G is 0. And then finally, after this, from G to infinity, the derivative is negative and getting more and more negative, so it'll be decreasing at a steeper and steeper rate. And so I get a graph that looks kind of like this. I hope this helps out. I know this is a little bit of a tricky concept. I know this was a long video, but feel free to comment below if you have any questions. If you want to see some more examples, I can try to pull together some more. If you have questions on other things here, please feel free to ask.